Hello, everyone. This particular session is for the research track students. At Cheenta, we have, apart from Math Olympiad and ISI, CMI entrance and college math program, we also have a research track program for advanced students who are interested to learn advanced mathematics and maybe discover something on their own. So we have small groups of researchers who lead these projects. Even school and college students do this. This is a fantastic program. We're trying this since the last 1 year. It has progressed a little bit. So I'll talk about the one of the problems that we often think about. This is in my research track. So I am studying geometric group theory. I'm extremely interested in groups and to understand them in terms of geometry. One of the things we are very interested in are known as geodesics, which are shortest paths. So I'll give you an example. This is about walking on the torus. So you are all familiar with the donut, maybe. You have seen the donut. It kind of looks like this particular shape that we have drawn on the picture. Now suppose there is an ant, maybe I can use a different color. Suppose we have an ant on the surface of this donut. An ant on this surface of this donut. And this particular point is A. And suppose here is another point B. So there are 2 points on the torus. One point is A, another point is B. A natural question is this. Suppose the ant wants to go from A to B. How will it go? Like, what is the shortest path that it will take to go from A to B? This is a very natural question if you think about it. I mean, in fact, people who like geography, they think about this problem all the time. If you want to make a map of the world, you want to find the shortest path from one country to another if you are traveling on the globe. And naturally, it's a sphere, so you have to think about it in a different way than you think about it for a plane. So about paths on a plane. So suppose if we have a sphere like this, maybe. So if we take a point here as A, and here is another point B on the surface of the sphere, a natural question would be, what is the shortest path? What is the, oh, I see Navneet is here. Hello, Navneet. Thank you for asking the question. Yes, we do have a program for RMO. Admission is going on. You can check in our website. Okay, so how would the particular person go from A to B on the surface of the sphere? So one thing you really want to do is to find the shortest path from A to B. It's a problem of mathematics, and it has been used by geographers all the time. Now suppose you are not on a sphere. Instead, what if our world was like a torus? I mean, what if our world looked like this? Maybe our world looks like a donut instead of a torus. So how will it go from the point A to the point B? How will the ant or a person, if standing on the surface of the sphere, or a torus, go from the point A to B? So this is a question that people have wondered over and over again. And in fact, not all spaces will have this kind of shortest paths. So in some spaces, you can talk about shortest paths. So then they are called geodesic spaces. And in some spaces, you cannot talk about shortest paths. And the spaces where you cannot talk about shortest paths, those spaces are called non-geodesic spaces. Okay. So I'll tell you a method to find the shortest path on the torus. And this particular method works for a general class of spaces. So this is a general strategy. And what is it? Let's talk about it. So this strategy is like this, that if you have, I'll take a square sheet of paper. So you have A, B, C, D, the square sheet of paper. And what you do is, okay, maybe I can erase this. Okay. And what you do is you glue AB with DC, glue AB with DC, and you glue AD with CB, AD with CB. So glue AD with BC and AB with CD. Okay. So if you do that, what do you get on the surface of this? What kind of picture do you get? If you glue AB with DC, you will get a cylinder like this. You'll get a cylinder like this, and maybe this dotted path is AB with, and this A and this is D, suppose, and this is B and equal to C. So they are glued up, AB with DC. And then if you glue them back, you get the torus. You get the torus. So you should be able to think about this in your mind, that you first fold the paper. Maybe it's made out of rubber. It's a rubber sheet. So you glue AB with DC and you glue AD with BC. So you now have this kind of a torus. Okay. Now suppose you were on this point X on this square sheet of paper, and you want to go to the point Y. So you are on the point X and you want to go to the point Y. The question is, how will you go? How will you go from X to Y? So one thing you can do on the square sheet of paper is that you can draw a straight line from X to Y. You can draw a straight line from X to Y, and that is definitely one path. This is one path. This is one path. X to Y, this straight line. But there is actually a shorter path of doing this. There is a shorter path of doing this. On the torus, there is an easier way to do this. How? Well, what you can do is you can actually move toward AB. You can move toward AB like this. So suppose this point is M. This point right here is M. And M is glued to this M prime. M is glued to this M prime. So you move from X, you move toward AB, you reach the point M, but after all, M is M prime, it is glued together. Remember, AB was glued to DC, and then you sort of magically appear at the point M prime, and then you move to Y. So this is another shortest, this looks like a shorter path than the one that we just talked about, the XY direct straight line. So on the torus, due to the gluing, there is actually a shorter path than the segment XY, So there is a shorter path. The pink path right here is shorter than the XY direct segment, the yellow path, right? So the question is, how do we measure the shortest distance between X and Y? The shortest distance between X and Y. So what we will do is, we will talk about something called discrete walks. Discrete walks. Discrete walk on the torus. So how does the discrete walk works? Well, what you do is you take a point. So this point is X. let's call it x0, and the final point is y, let's call it yn, so the nth point. So this is a x0 and yn are the two end points, and n is finite. So basically n could be 20, for example. And what you do is you take the distance. Okay, so maybe I can write it like this. You take the distance like this, x0 to y0, which is equivalent to x1, y1, which is equivalent to x2, like this, up to xn. So you have these continuous sequence, this sequence of points, and you measure the distance between those 2 points. Now, the way you do it is quite simple. What you do is you think about these 2 points, y0 and x1. These 2 points are glued. y1 and x2. These 2 points are glued. And similarly, yn minus 1 and xn, these 2 points will be glued. So when you take points, subsequent points will be glued. That's how you take the path. That's how you take the path. So that's how you measure the distance. So let me just write it, then you will see what I'm saying. You will measure the length. Okay. You will measure the length of the distance between x0, y0 plus the distance between x1, y1 plus the distance between x2, y2 up to the distance from xn, yn. So this will give you a particular number. x1, x0, y0, x1, y1, x2, y2 up to xn, yn. You measure these distances. Suppose this value is called L1. So what you do is you take all possible discrete such discrete walks. You take all possible such paths. Take all such paths. And you take this infimum of that. You take all such paths and you take the infimum of all those paths. Infimum is like the minimum. It's not the minimum. It's the smallest value, smaller than which you cannot get those numbers. So you take all such paths and then you take the infimum of that, and that becomes the distance between x and y. So that becomes the distance between x and y. So for example, in this picture, I could say x, take xm, and m prime y. Take this. So I have dxm plus dm prime y. This is my discrete walk in this particular case. Dx to m, so this point is x. Here you have x, here you have y. So dx to m and then m prime to y. So you have dxm plus dm prime y. So these two things together give you the discrete walk. This is one of the discrete walks. This is not all of them. This is just one. Okay. Now the point is this. This is a very interesting thing, that this particular x to y distance, the number that you get, the infimum that you get, that infimum, the distance function that you get using that infimum may not be a proper distance function. So you have to be very cautious. Those who understand what is a proper distance function or a proper metric. I mean, I don't have time to explain what is the meaning of a proper metric here, but what it really means is that this distance function may not be quite similar to the notion of distances that we have in real life. So it can differ from it slightly. It's a very interesting subject when you move from actual metrics to proper metrics, and you sort of understand. So from actual metrics to improper metrics. So you see the subtlety in there, and you see, okay, maybe this is not always a metric. But the point is that in any type of surface that is constructed like this, using this gluing method, there you can create at least an improper metric using this discrete walk. So that's the key idea. I wanted to share it with you. You can keep on watching beautiful videos and doing beautiful mathematics. Stay well and stay home. This is a very difficult time, but we should all be happy and doing mathematics at least. All right, take care. Bye, all of you.